Hello everyone, this is A. Sarishka from 2nd CSCA and my registration number is 22B01A0504. And this is Dara Mamshita Lakshmi and my registration number is 22B01A0531. And our topic is thread libraries.
First of all, what are threads? Threads are indeed individual units of execution within a process. They are the smallest sequence of programmed instructions that can be scheduled by an operating system scheduler. Each thread within a process has its own program counter, registers, and stack, which enables it to execute code independently and maintain its own state. Threads within a single process share the same memory space, allowing them to communicate and share data more easily than separate processes. This parallelism and shared memory make multi-threading a powerful technique for improving the efficiency and responsiveness of software applications. Now let us see how threads are essential for concurrent execution. Threads are fundamental for concurrent execution in an operating system. They allow multiple tasks to run concurrently within the same process, enabling efficient resource utilization. Threads share the process's memory space, making data sharing and communication easier compared to separate processes. Multithreading. Multithreading is the concurrent execution of multiple threads within a single process. Threads are independent sequence of instructions that can be executed concurrently, allowing a program to perform multiple tasks in parallel within the same process. Significance of multithreading. Multithreading maximizes the use of modern multi-core processors. Threads can run on different cores, improving overall performance. Multithreading keeps the user interface responsive during background tasks. Improved resource utilization and efficient program execution are advantages of multithreading. Threads are two types, user-level threads and kernel-level threads. User-level threads. User-level threads are threads managed entirely by user-level libraries or applications. ULTs are lightweight and do not require kernel support for thread management. ULTs are suitable for applications that need fine-grained control over thread scheduling. Now coming to the pros of using ULTs, lightweight and efficient, highly portable across operating systems, offers developers full control over thread management. And cons of ULTs are limited multi-core utilization, lack of key OS features like input-output blocking, risk of entire process blockage due to blocking ULTs. Kernel level threads. Kernel level threads are also known as KLTs. KLTs are managed directly by operating system's kernel. Each KLT corresponds to a separate execution unit with its own program counter and registers. KLTs offer true parallelism as they can run on separate CPU cores. Coming to the pros of kernel level threads, KLTs fully utilize multi-core processors for maximum performance. They can utilize important kernel features like input-output blocking and prioritization. Misbehaving threads do not affect the stability of other threads, ensuring system reliability. Cons of kernel level threads. KLTs come with additional overhead due to kernel management, making them less lightweight. KLTs may be less portable as they depend on varying kernel support across different operating systems. Developers have limited control over thread management as it's handled by the kernel. Thread models. Thread models are the strategies used to map user-level threads to kernel-level threads. Different models determine how ULTs are managed and scheduled by the operating system. Many-to-one model. In many-to-one model, multiple user-level threads are mapped to a single-level kernel thread. ULTs share the same KLT for execution, which means they run sequentially on that KLT. ULTs are limited by the behavior of the single KLT. It underutilizes the multi-core processors as ULTs run on a single core. One-to-one model. In the one-to-one model, each user-level thread corresponds to a separate kernel-level thread. Each user-level thread has its own kernel-level thread, allowing them to run concurrently on separate cores. Have a look on the diagram. It offers maximum parallelism, efficiently utilizing multi-core processors. It has higher overhead due to the management of multiple KLTs. Many-to-many model. In the many-to-many model, strikes a balance between the one-to-one and many-to-one models. It provides a flexible approach to mapping user-level threads to kernel-level threads. It offers a balance between parallelism and resource efficiency. Have a look on the diagram. You can understand somewhat better. Thread libraries. A thread library provides a programmer an API for creating and managing threads. There are two ways to implement these thread libraries. The first one is to provide a library entirely in user space with no kernel support. In this way of implementation, all code and data structures for the library exist in user space and every function call executes in user mode, not in kernel mode. And the other way of implementation is to implement a kernel library supported by OS. In this, all code and data structures exist in kernel space and invoking functions result in a system call to the kernel. The three main thread libraries are POSIX pthreads, Win32 threads, and Java threads. POSIX pthreads are often used in Solaris, Linux, Mac OS, and through 64 Unix. Win32 threads are used in Windows and Java threads are used in Java. POSIX pthreads. POSIX threads, often referred as pthread, is a standard thread library for Unix and Unix-like operating systems. It provides a consistent API for creating and managing threads, making it widely used in Unix ecosystem. Pthread enables multiple threads within a process to run concurrently. It allows developers to harness the full potential of multi-core processors, improving the system's performance and responsiveness. By supporting thread-level parallelism, pthread contributes to efficient resource utilization. It helps applications efficiently use CPU cores, memory, and other resources. Pthreads is a standard set of C library functions for multi-threaded programming. Pthread library contains 60 plus functions. Programs must include the file pthread.h. Programs must be linked with the pthread library. Creating threads using pthread libraries. Have a look on the code. We have included necessary header files including stdio.h for standard input and output and pthread.h for pthread functions. We have defined a thread function void star thread underscore function void star arg which takes a single argument and integer thread ID. These functions print a message indicating that a particular thread is running and then returns a null pointer. In the main function, we declared an array of three pthread underscore t objects named thread to represent the threads. We have created an array of three integers named thread underscore args, each containing a unique thread ID 1, 2, and 3. And then we have used a loop to create three threads. The next line creates a new thread and associates it with thread underscore function. It also passes the specific thread argument, which is the address of the corresponding element in the thread underscore args array. And then we have used another loop to wait for each thread to finish its execution. The line pthread underscore join thread id null waits for each thread to complete its execution before proceeding. It ensures that the main program does not exit until all threads have finished. The program then returns 0 to indicate successful execution. This code demonstrates how to create and manage multiple threads concurrently using pthreads, each executing the thread underscore function. The thread underscore args array is used to pass the thread specific data to each thread. This allows you to perform the thread specific tasks or differentiate between different threads. We can see the output of the given code. Thread 1 is running, thread 2, 3 is running, thread 2 is running. So now coming to the Win32 threads, the first point is that Win32 threads provide function like create thread for creating threads in window applications. And the second point is that they offer various functions for synchronization, priority setting, and thread termination. And the third point is that Win23 threads enable concurrent execution in Windows applications. And also we know that they provide mechanisms like mutexes and semaphores for resource access control. And also, we know that developers can assign priority levels to threads to control. And coming to the next point, here we discuss about the Win32 threads are kernel level managed by the Windows kernel. Internal to Windows, API programming can commonly used in C, C++ languages. And also, we know that one function needed to make one functionality and it is simpler and more generic. Coming to the next point, it has only one data type, that is handle, crucial for real-time applications with precise timing, and also requires attention to synchronization and error handling. So coming to this slide, it tells us about creating a threads with Win32 threads. In this, the first two lines tells that these are the header files that include necessary declarations for standard input and Windows API applications. And then this function serves as the entry point for the threads that will be created. It makes a single parameter, LP param, which is a pointer to a parameter. In this case, an integer representing the thread's ID, the function prints a message indicating which thread is running and returns 0. And coming to the int main, this is the main function where the program starts. And here we use a thread handles called handle, an array of handles to be created threads. Handles are used to manage and control the threads. And now in thread args in square brackets 3 defines that an array that holds the arguments, in this case thread IDs for each thread. And now inside a loop that iterates 3 times, threads are created using a create thread function. Each thread is assigned to the thread function and the corresponding thread ID is passed as a parameter using and thread args in square brackets I. The create thread function returns a handle to the create thread which is stored in thread handles in square brackets I. And also after creating the threads, the program waits for all the 3 threads to complete using wait for multiple objects with the finite time output. And now meaning it will be wait indefinitely until all threads finish the execution. And finally another loop is used to close handles of the threads to release system resources. The close handle, in the summary of the code, it tells that the 3 threads that each run the thread function passing a unique thread ID as a parameter. It waits for all the threads to complete before closing the thread handles. This demonstrates a basic multi-threading example in a Windows environment. So this slide tells us about Java threads. Coming to the first point, Java provides a robust thread management system that allows developers to create and manage threads within their applications. And the second point tells us about the multi-threading is a fundamental feature of Java enable concurrent execution of tasks. Threads in Java are created and managed using the thread class. Coming to the fourth point, it tells us about the developers can extend the thread class or implement the runnable interface to define the behavior of their threads. Java also provides methods like start, join, and sleep for thread control. It also offers various libraries and APIs for advanced thread management. Java.util.concurrent package provides tools for thread synchronization, concurrent collections, and high-level concurrency constructs. And also, libraries like Executor Service and Fork Join Poll simplify the creation and management of thread pools. And also, the Java thread related libraries help developers optimize the performance and resource usage in managed by JVM. Creating threads with Java threads. Coming to the first line, this is the declaration of a public Java class method. Simple thread example. The public static void main tells that it is the main method which serves as the entry point of the program. The two threads, thread 1 and thread 2, are created using Java's thread class. Each thread is initialized with a lambda expression, a type of anonymous function that simplifies the code to be executed by the thread. The code inside each thread runs a simple loop from 1 to 5, printing a message that indicates the thread number and the current count within the loop. Thread1.start and thread2.start. These lines start both the threads. The start method is used to initiate the execution of a thread. It does not run the thread immediately but schedules it for execution. When you run this program, the two threads, thread 1 and thread 2, will execute concurrently. They will both print their respective messages in an interleaved fashion as they are running simultaneously. The actual order of execution may vary, but you typically see something like the code which is present on the slide and the output on the slide. This code demonstrates the basics of creating and running multiple threads in a Java program, allowing for concurrent execution of tasks. So the next slide is all about thread synchronization. Thread synchronization ensures safe and orderly execution of multiple threads, preventing issues like data corruption and race conditions. It's viral when thread shares resource. Common scenarios includes shared resource access, producer-consumer coordination, protecting critical sessions, and thread communications. Mechanisms like mutexes and semaphores control access and cooperation. Proper synchronization makes programs reliable and less prone to concurrency bugs. Common situations where thread synchronization is important that includes shared resources access, producer consumer problem, critical sections, and the thread communications. The thread synchronization is vital in multi-threaded applications to ensure data's consistency and prevent race conditions. Synchronization mechanisms help coordinate the execution of threads, making the program safer and more reliable. Common synchronization mechanisms. The first one is the mutexes, the mutual exclusion. Coming to the first point, mutexes allow only one thread to access a critical section of code at a time. They prevent multiple threads from modifying shared resources simultaneously. Semaphores. These semaphores are used to control access to a limited number of resources. They enable coordination among threads by signifying whether resources are available or tasks are completed. The condition variables. Condition variables are used for thread communication and synchronization. They allow threads to wait for specific conditions to be met or to signal when the conditions change. Selecting the appropriate synchronization mechanism depends upon the specific requirements of the application. Common challenges in multithreading. The race conditions. These occur when multithreads access shared resources simultaneously, leading to the unpredictable and incorrect results. For example, two threads may read and modify a variable concurrently, causing data inconsistencies. Deadlocks. Deadlocks happen when threads become stuck in a state where they are waiting for each other to release resources, resulting in a standstill. This can occur when threads complete for multiple resources and each thread holds some while waiting for others. Data corruption. Data corruption arises when threads concurrently modify shared resources without proper synchronization, leading to invalid or corrupted results. Strategies for multi-threading challenges. Coming to the first point, mutexes and locks ensure exclusive resource access. Thread synchronization, coordinate thread activities, thread safe and data structures, minimize data corruption risks. Critical sessions, protect shared resources, avoid circular looking, prevent deadlocks, thread coordination, prevent indefinite waits, testing and debugging, identify and resolve issues. And the conclusion is that the thread libraries are essential for modern computing. User level threads, UTLs, offer portability but limited parallelism. The kernel level threads provide full parallelism with higher overhead. Java threads and advanced libraries enhance concurrencies. Challenges include race conditions, deadlocks, and data corruption. Proper synchronization and thread library selection are critical.
Thread libraries are a key to efficient and responsive operative systems, optimizing multi core processor usage. Thank you.